Okay, let's start again. The previous class we tried to set the wave function, but finally we in this chapter we finally trying to find what wave function is, and then we will derive the exact form of the wave function. And then before that, in the general form, so we try to set wave functions boundary condition. Okay. So those are the boundary condition of the wave function. And for example, this is something kind of the boundary condition. This is the wave function square function. And then you already know the wave function square is proportional to the probability, right? The finding probability for the better understanding. So if Jungsu's particle has this wave function, and then we can expect where Jungsu is now based on this Jungsu's wave function square function, right? So Jungsu should be in anywhere inside this universe, right? So all of the probability to find Jungsu in this universe is 1, like 100%. Jungsu definitely inside in this universe. The probability percent to find Jungsu in this universe is 100%. That is some kind of the boundary condition. Like for example, we don't know, but maybe if we integrate this wave function or wave function square from minus infinite to plus infinite, definitely that value is same to 1. Okay, that is a wave function. So that is the boundary condition. So if you have one boundary condition, you can find one unknown value. You understand? Like that is some similar to 연립방정식. 영어로 뭐지? Well, if you have the two different equations, and if you have two unknown value, you have to have at least two equations to find the two unknown value, right? So if you have one boundary condition, you can find the one unknown value. So those are all of the boundary conditions, okay? So let's try to find the wave function. Well, we don't know what is exact shape of the wave function, but we know what wave function is. And then wave function scale is proportional to the probability, right? And then all of the particle is composed of, could be presented in the wave, in a wave function. Let's try to make it easier. And the most easiest wave function form is sine curve, right? That is the most super easy wave function form. So this is the sine curve, and this is the typical sine curve equation, sine curve function. So we have to consider angular frequency, right? Omega. And then like here is v, but we need to consider wave number k, okay? Omega and k, you remember that? So our assumption is a free particle. So what we are now trying to find the wave function of a particle, and then our assumption is this is the free particle. Free particle means a particle that is not under the influence, like under other potentials, other interaction with under influence of any forces, and therefore pursued a straight path at a constant speed. That is not under any forces or any condition. So that means you have a particle is moving, there is no force and no potential or no energy around that. So the speed of this particle is unchanged, and then moving this way, the direction of the moving is not changing because there is no forces, no pressure, no energy, no electrical potential, no gravitational potential. You understand? So this is our assumption. So that looks like this. So undamped. That means this wave function should have constant amplitude, A. Amplitude is not changing because that is undamped. Monochromatic. One wavelength is existed. There is no various kind of the wave function, only one kind of wave function. That is the monochromatic, and then that means constant angular frequency. Kind of frequency is just one, only one kind of frequency, right? That's right. So this is the Maxwell equation. So this one. Well, typically we have to consider the three-dimensional case, but we only trying to handle just one dimensional case. And then this is the wave, the Maxwell equation, and then the roots of this equation. This is like the 갑자기 뭐냐? 갑자기 뭐 단어가 갑자기 기억이 안 나네. 미분 방정식, differential equation. So this is the differential equation. This is the double prime, right? Look at this. This is the double prime. This is the double prime by x, double prime by t. The two different variables, and then differential equation. If you solve this differential equation, we can get a root, and that root looks like that. Y equal a exponential minus I omega times t minus x over w, x over v. Okay? Well, you don't need to understand that one. You just accept this because this is the very famous equation. Okay? So this is the rule for the exponential function, and then I, and then exponential minus I theta could be written in cosine theta minus I sine theta. Okay, that is the rule. And then just by using this, we can change this equation to this form, cosine and sine term. Y equal a cosine omega times t minus x over v, right? And then minus ia sine omega times t minus x over v, the velocity. So this is the form. This is the wave function from our assumption, right? Okay, let's take a look at this. So we have this wave function, right? This is the opposite way to prove this wave function is a root for this. Okay, so if this equation is a root for this differential equation, if you put this number into this differential equation, that should be, this differential equation should be valid. Okay, this is the root. So if you differentiate this function by x, and then this looks like that, right? So differentiate this by x. Where is the coefficient in front of the x? I omega over v, right? That is the coefficient of x. So coefficient of x is located in front of the y, in front of this exponential function. You know that, right? This one. Remember that, right? So the I omega over v and also this is the same, and then differentiate this again by x. So you have to pay attention because there is the two different variables, x and then t. So if you try to differentiate this function only by x, t is constant. If you trying to differentiate this function by t, x is constant. Understand? So another additional differentiation on this, and then we just multiply this again, I square omega square v square, right? So I square is -1. So minus omega square over v square y. So this is the this term. This is the result of after the second order differentiation on this y function. We now calculate this. Okay. So this we trying to differentiate by t. So take a look at what is the coefficient of t, minus I omega. That is the coefficient in front of t, minus I omega. And then this is the I square, omega square, right? So finally, the coefficient is minus omega square y. So this is this term, right? So let's take a look at our previous term. This is minus omega square over v square, and then this term is minus omega square, and then we have to add it 1 over v square to make these are equal. Okay, so that means this is the function of this. This is the root of this differential equation. You understand? Okay, let's set this function to wave function. So we just put this function to wave function. What we usually call the wave function psi. Okay, so omega is 2 pi nu, right? Omega is 2 pi nu, and then v equal lambda nu. We just shift these two variable using this, and it looks like that. And then energy E equal hanu. So we can change 2 pi haba nu, because the haba is same to ha over 2 pi. And the lambda can be written in ha over p according to de Broglie equation, right? And then we can say lambda is 2 pi haba over p. Okay? And then we just change this number, the value using this value. And then psi could be written in a exponential minus I over haba and et minus px. Okay? Et minus px. So E equal this number, and then omega is the 2 pi nu. So we can change E equal haba omega, P equal haba k. So we can also write down this wave function a minus exponential minus I omega t minus kx. Okay? This is something kind of the mathematical processing. Well, I strongly recommend you guys to write down this equation, this process, the several times to be familiar with this equation. This is the Schrödinger's equation. So this is the Schrödinger's equation. psi equal a exponential minus I over half times et minus px. Okay, there is two variable p and x, time and position. Okay, let's take a look at second order differentiation here. Second order differentiation on the psi, and then we differentiate this by x. What is the coefficient of x? Is IP over half, right? IP over half. So after the multiple differentiation, I square p square over half square. So minus p square and a half square. And then also we have psi here, right? So we can change this equation. P square psi is same to minus half square times d psi square over dx square. Okay? And then let's try to do this differentiation by t. What is the coefficient of t? Minus I e over half, 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 this one. So energy times psi could be written in minus half over I d psi dt. Okay? You understand? And then we have this also the general equation. This is the energy, total energy. Total energy could be written in kinetic energy and then potential energy. We don't know what is the potential energy is. Maybe potential energy could be like electrical potential energy or the gravitational potential energy, maybe some potential energy, okay? So this is the kinetic energy. Let's multiply psi, left side and right side. E psi equal p square psi over 2m plus u psi. We already obtained this e psi and then p square psi, right? From here. We just put into e psi, this to here, and then p square psi to this. Okay? So finally we found this. I half times d psi dt is same to minus half square over 2m. And then this is, well, we use the only x here. We can extend our x to the other three-dimensional value. So this is the time-dependent form of the Schrödinger's equation in the three-dimensional. We don't know wave function, but this is the differential equation, Schrödinger equation. If you solve this Schrödinger equation, this is the differential equation. If you solve this Schrödinger equation, you finally obtain a root. You finally obtain a function. You finally obtain a wave function, psi. We don't know, but you can just put a lot of boundary condition, and then you can solve this Schrödinger equation according to that boundary condition. Finally, you obtain psi. Like this is the same process. This we don't know, but we have differential equation here. If you solve this differential equation, you finally obtain this wave function. This wave function can show this sine curve, right? So in the opposite direction of the wave, so we just put into our wave general form of the wave function, and then we found we fabricated the differential equation to obtain wave function. Okay? You understand? No? Well, typically, you have this equation. This is the equation, right? So after solving this equation, you obtain some like root plus minus k, right? This is the root of this equation. We don't know, but finally we trying to obtain psi. We don't know. And then also how we can obtain this wave function. We don't know differential equation to obtain this. So we make this and then trying to find this differential equation. Schrödinger equation is this differential equation. And then we try to find psi, what psi is, okay? You understand? So this validity of the Schrödinger's equation. Schrödinger's equation cannot be derived from the other basic principle of the physics. That is the basic principle itself. And then what we must do is postulate Schrödinger equation, solve it for variety of the physical situation, and then compare the results of the calculation with results of the experiment. So we have this. This is the Schrödinger equation, right? So we try to solve this Schrödinger equation according to a lot of the physical situation. In a lot of the physical situation, we have a lot of the boundary condition. And finally, we obtain the wave function. So what happened is that Schrödinger's equation has turned out to be remarkably accurate in the predict the results of experiment. So after solving this Schrödinger equation, and we can obtain the wave function, and then the results are exactly the same to the experimental condition, experimental result. So Schrödinger equation does not increase the number of principles need to be described the working of the physical world. For example, F equal ma can be derived from the Schrödinger equation. Well, Schrödinger equation can include the large area of the physics. So we can directly derive the other classical mechanics equation from the Schrödinger equation. Okay. Okay, so let's take a look at very basic property of the wave function. Okay. So this is the linearity of the wave function. If you already took differential equation class, you already know about this. If you have the two different roots, psi1 and psi2, psi1 and psi2 is also a root for any differential equation, solution for the wave function, and also another psi, linear combination, psi equal a1 times psi1 plus a2 times the psi2 is also another solution for same differential equation. So you already know about this from differential equation class. 미적분학 배웠죠? 그래서 나온 거야. And then so this is the superposition of the wave function. So first of all, you can just imagine this electron diffraction. So we have those two slits, and then electrons are coming, and then this is the screen. And then psi square is the probability, right? So psi1 and psi2 are all of the solution for the differential equation. Psi2 square is psi2 complex conjugate times the psi2, right? And then psi1 square is psi1 complex conjugate times psi1, okay? So if you have the two different slit, so this is not the results. Probability is not obtained from psi1 square times psi2 square. That is not obtained from directly by using this, because we have to consider linear, the combination, and then superposition. So we have to obtain this, not psi1 square times psi2 square, but we have to we have to try to calculate psi1 plus psi2 square. Okay, so the result is psi1 square times psi2 square plus psi1 complex conjugate psi2, and then psi2 complex conjugate and psi1. So if you draw this result, the result looks like that. This is exactly same to our experimental result. Electron diffraction, okay? Because electron is a particle at the same time a wave, okay? So let's take a look at expectation value. We are now continuously talking about the probability. So, but we need to change the probability to the expectation value. So the expectation value is the predicted mean value of the results of an experiment. If you are doing some experiment, you may expect most probable value. That is the expectation value, right? Like for example, Jae is coming to university, and then Jae should every day Jae usually arrive at university 9 a.m. Well, sometimes Jae arrived at 8:45 or 8:58 or 9:10 or the different time, but most probable time is 9. That is the expectation value. You understand? So expectation value, most predicted mean value of the results of experiment. So discrete value, if you have a discrete value, so expectation value can be obtained by this equation. N is the number of events. X1, X2, X3 as the mean, X2 is every single value. So you can just think about, we are now trying to measure Jae's commuting time. What time is the most probable time to Jae in this university is, we try to do that. And then Monday, Jae arrived 8:45. Tuesday, Jae arrived 8:40. Wednesday, Jae arrived like 8:50. Or Thursday, maybe Jae arrived at 9:10, right? So we have a lot of the time split, like 8:50, 8:55, 9:10, 9:20, something like that. And then we trying to count how often, how many times, how many is the event, how many times for the event. 2 times for this time, 3 times for this time, 1 time for this time, 5 times for this time. How we can obtain that? Multiply this, add it up everything, multiply this, add it up everything, and then divide by total number of events. So if you count like 10 times to trace the J's commuting time, you have to divide by 10. And then finally you can obtain expectation commuting time. You understand? You understand? So this is the discrete value. If you have a continuous value, so this is the events, number of events, but this is the probability for this event. P is the probability for that event. Okay, the same. Probability and then event value, probability event value, probability event value, probability event value. So at the bottom, so we added all of the probability. Well, typically what is the all of the probability? What is the summation of the all, sum of the all of the probability? 1, right? So this should be 1. And then also we can obtain the probability, pi can be obtained from the psi square, right? Psi square. So the expectation value of a position of single particle, if you have a particle, we can expect where is the particle, most probable position of this particle at this time. We can expect it that. So expectation value can be obtained by x times psi I square plus x times psi I square, and then we sum all of things, and then this is the total probability value. But you already know this is the 1, right? So this is normalization process. This because this is the 1, and then expectation value is this. Okay? You understand? So can be used to obtain expectation value of any quantity gx. So if you are interested in, well, for this case, we are curious about the position. So if you're interested in other value like momentum, you can just put into momentum value and then with this wave function square. We don't know the wave function, but if you obtain the wave function, you can utilize wave function for a lot of things. You understand? I guess. So these expectation value are very, very important. Okay. But in the previous chapter, no, I mean, so the chapter before that the previous chapter, uncertainty principle, the expectation value P, expectation value for momentum, cannot be calculated this way because according to uncertainty principle, so there is no function P as a function of X because we don't know both of value, position and the momentum at the same time. We don't know that. So momentum is not as a function of position. You understand? So this cannot be existed. So we specify X so that the delta X is 0. We cannot specify corresponding P because delta X times delta P should be larger than half over 2. That is the uncertainty principle. Same problem for energy and time. Delta E times delta T is larger than half over 2, right? How we can obtain P and E? How we can obtain momentum and then energy? Well, you have to pay attention. Inside the Schrödinger equation, there are 2 different variables, position and then time. Because you are using position and time, you cannot obtain the momentum and then energy from this wave function equation. This is the operator. I love this point. I love the section in this model physics. This is the very, very, very interesting approach. Okay, let's take a look at this equation. This is the wave function equation, right? The first one. This is a wave function equation. Okay. If you differentiate this wave function by x, because due to the property of the exponential function, you can easily obtain this, right? We only take a look at what is the coefficient of x. What is the coefficient of x? Minus plus p over ha. Oh, this is I. Minus IP over half, right? Right? You understand? So we can just easily shift this P half, P psi. P psi is this value. We don't know P, we don't know the wave function, but if you want to obtain P, first of all, you have to differentiate this psi, differentiate psi by x first, and then multiply half over I to that result. And then that result, you just remove psi. If you just remove psi, the remains should be momentum. 제이 알겠어? So we obtain this. We have this wave function. If you differentiate wave function, so we can obtain this, right? And then we change this equation to this. Multiply half over I. And we obtain this equation, right? We obtain this. Huh? So in the left term, P psi, this is the momentum. We don't know what momentum is right now. But to obtain the momentum, if you have the wave function psi, first of all, you have to differentiate wave function by x, 미분, x로, and then multiply by half over I. So you finally obtain something from this calculation, right? And then that calculation is same to P psi. So if you remove the psi from this equation, this result, the remains, 남는 거, is P. Okay? So in the same way, differentiate psi by t, and then the coefficient is minus I over E over half, and then E psi is I half times d psi dt. The same way, if you want to obtain energy, first of all, you just differentiate your psi, your wave function by time, and then multiply I half. And then from the result, you just split. This is the psi term, and then the remaining term. The remaining term is energy. So the momentum operator is P, that is the half over I dx. Energy operator, I half times dt. So that means if you have a wave function, you just added up this and you can obtain energy. You just added up this, you can obtain P. So energy is composed of the kinetic energy plus the potential energy. So the kinetic energy is P square over 2m, right? And then, so this is the momentum operator, right? Square, and then half square, and then I square is minus 1. So this is the kinetic energy operator, right? So this is the kinetic energy operator. So the energy operator, this is the energy operator, right? This is the energy operator. Energy operator here, kinetic energy operator here, and then plus potential energy. So this is the total energy operator. If you multiply psi into here, that is the Schrödinger equation. Okay? So we just put this potential energy just to U because there are the different type of the potential energy. But compared to the potential energy, the kinetic energy is very obvious, right? only one kinetic energy. Okay? So expectation value of the P and E. So expectation value for momentum is, so this is the expectation value equation, right? This is the expectation value equation, right? Psi square times some function. So we have momentum operator, and then this is the square, and then we just put into this momentum operator, and then we can just change our equation. Half over I is constant, and then we just put it out, and we just put this, okay? And then energy operator, because I half is constant, and put it out, and just leave it this. So when differential operators are involved, the correction order of the factor must be observed. So if you put this operator, calculation order is from this right to left. This first, and then this. You understand? This first, and then this. Right first, and then next, left, left, left. Okay. So expectation value of an operator. So if you have operator, you can just put into this. Okay. So psi complex conjugate and psi is the psi square. So if you want to do some operation on it, you have to put this operator between these two complex conjugates. Okay. So we already obtained this Schrödinger equation, but this is a function of time and position at the same time, right? That is very complicated to solve this. So most of cases, so we assume we just see steady state. There is no change of time. We only keep focused on change of position. That is the Schrödinger equation steady state form. So we have this wave function, right? We can split this wave function two different forms. Minus t term, time term, right? Here is time term, and here is position term, right? You understand? So this is the time term, and then this is the position term. The small psi is contain only position term, and then multiply by e minus ie over half t. This is the time term, right? So you just put into this large psi into Schrödinger equation. You can multiply this small. This is only contain position term. Only contain position term. You can just easily remove this time term. Okay. And if we can just easily remove this time term, divided by exponential term, this time term. Only we have this energy, small psi, minus half r over 2m, small psi, double, there is no term related with the time, right, here. And then we change this. D square psi over dx square plus 2m half square minus e minus u psi 0. That is the steady state Schrödinger equation in one dimension. So dx square d square psi plus 2m. 2m half r e minus u psi is 0. This is the steady state Schrödinger equation. Well, you don't remember, you have to pay attention. This is the differential equation. If you solve this differential equation, you can obtain psi. That is the wave function to describe particle motion. Okay? You have to keep your mind, right? Well, take a look at this. This looks like very similar to your differential equation class problem. Look at this. This is the y double prime plus, I don't know what that is, but this is a y equals 0. Very simple term. Well, you already know about a y, b y, 1 prime, c y equals 0, right? You already learned about how you can solve this differential equation, right? In the differential equation class. But before this case, there is no 1 prime term here. Okay? So this is the steady state Schrödinger equation in one-dimensional. Why we try to simplify this Schrödinger equation is, finally, this is the differential equation. We try to solve this differential equation to obtain a root. To obtain a root. Root is wave function, right? You understand, JE? So if you extend this steady state Schrödinger equation to three-dimensional, you can just change this term. Okay? So eigenvalue and an eigenfunction. So eigenvalue is the value of energy En for which Schrödinger steady state can be solved. Eigenfunction is the eigenfunction of the linear operator G defined on the sum function space in any non-zero function size that the space and return from the operator exactly as is. That is a very complicated explanation, right? So let's take a look at. This is the operator, right? Operator. And then wave function. Also wave function. This is the value we're trying to find, right? This is the energy value. This is the wave function operator. So we can call this function to eigenfunction. This value is the eigenvalue. But in the following the calculation process, you definitely meet, there are some quantum number here, psi 1 and psi 2, energy 1 or energy 2 or something like that. Okay? So a certain dynamics variable G, we don't know the G. G maybe could be the energy or the momentum, be restricted to discrete value Gn. G is the quantized. Well, in the many cases, if you solve that Schrödinger equation, you obtain the G value, like energy value or momentum value. That energy value is not the single value. That is the quantized value. So this is the eigenvalue equation. So Hamiltonian operator, that is an expression for the total energy of the system in terms of the coordinate and then momentum only. This is the Hamiltonian operator. Looks very similar to steady state Schrödinger equation. If you multiply this Hamiltonian operator to something, you can obtain energy. If you solve that, you can obtain the energy. This is the operator and quantity. Quantity position x, operator x, linear momentum, this is the momentum operator, potential energy is same, kinetic energy, this is the kinetic energy operator, total energy, this is the total energy. This is a total energy that is but different form, the Hamiltonian form. This is the operator to obtain the energy.